Wonderful. Okay, so we're now recording. So hello, everybody. Welcome. We have the June 10th webinar for Kilonova Catcher, and we have a new guest, never before seen. We have never heard of this man before, completely new to KNC. He doesn't know anything about it. Um, our wonderful primary investigator, wonderful PI, Dr. Damien Turpin. He's an astrophysicist and leads KNC, and he'll be talking about parallel missions and the GRB follow-up strategy of Kilonova Catcher and Ergo Grandma. You have the floor. Can you share?
I can share if you unshare.
Yes. Oh, it should be two sharing. Okay,
Ah, yes. Wow, wonderful.
perfect. All right, you have the floor. Thank you for your expertise and thank you for joining us.
Yes, thank you very much, everybody. So it's a great pleasure for me to have this meeting with you tonight. Well, or in the afternoon for people, or in the morning, depends where you are. Actually, I decided to make this talk about gamma bursts and the past missions over the past 50 years, actually, to try to give you some motivation and understanding on how this field is still a vibrant field of research in astronomy after 15 years of observations. And I will also try to give you some insights on what are the new missions that are coming into the field. You have a cartoon picture here of one of the two that I'm going to present, which is called ZVOM. And finally, in the last part of this talk, I will try to give you some insights also on how Kilonova Catcher can participate, join this research field, and how we can contribute significantly to this field. So the third part is maybe the part that is going to interest you, because it's going to be kind of concrete part with advices for observations and where we can put our strengths all together on this field. But let's start with the first part of this talk. Before I introduce the newcomers in the field, new missions, space missions in the GRB field, I have to actually introduce a bit of the whole history of GRB missions and what are gamma bursts also. Just because actually gamma bursts are really an observational science. I will show you later, but this science really appeared through the serendipitous observation of the sky. So there were no theory before. And so we got observation of gamma bursts and we had to build everything from scratch. And so all the missions that are coming now into the field are actually inspired by the past missions. That's why it's really hard sometimes to introduce a GRB mission without introducing the others over the past years. So let's go for this exciting story that actually started during not a very, well, exciting times during the Cold War, actually. Um, you have to know maybe a little bit of history that, well, in the 60s, the USA, UK, and the Union Soviets, they signed a treaty in Moscow to ban the nuclear test. And one of the most important, let's say, line in this treaty was that this nuclear test should not happen anywhere on Earth, but also in the atmosphere and beyond its limit, including the outer space. And so, 6 days after signing this treaty, the US military launched two spy satellites called the Vela satellites. You have a picture of those satellites here on the left. And actually, they were equipped with gamma ray detectors on board. And the goal of those two satellites was to potentially detect nuclear tests in space. And so they were expecting very special, very specific signature for nuclear tests, for nuclear bombs. And so they were maybe expecting some Russian tests in space. And what they got actually in the 60 in the July 2nd of 1967 is this event. So one of the Vela detected this what we call now gamma burst. So you can see on this light curve you have the x-axis of the time. You have the time in seconds, and you have the number of counts that have hit the detector, the gamma ray detector. So a gamma light that have been shining into the detector. You can see a different structure in this light curve, but what is interesting is that this kind of light curve or emission is totally off compared to what you expect from a nuclear bomb. So, well, they didn't know what this signal was. They were searching if it was coming from the moon, because maybe some nuclear tests could have been made behind the moon or in the surfaces of the moon, if it was coming from the sun or something else. And so this kind of detection, gamma ray detection made by these Vela satellites were kept secret. And at some point in the beginning of the 70s, the scientists well, then released this publicly. And well, astrophysicists start to actually study this kind of phenomena that was completely new, unpredicted before. And so this was completely a new field to develop at that time. So there were several observations by Vela satellites and other satellites, well, with a low detection rate, so few events, well, not even localized in the sky or very poorly localized in the sky. But they started to make science, actually, very interesting science from these first detections. So I'm not going to give you all the details of this, but actually in the 70s there were and the 80s there were already a lot of science extracted from these first events. So I will jump directly into the 90s with the NASA mission called the Compton Gamma Ray Observatories, which is a huge satellite. You can see the arm here of the space shuttle that is one of the last, I think maybe one of the last flight of the space shuttle, I don't know. That was releasing actually these big quantum gamma ray observatories. It was not designed totally for gamma ray bursts, but they equipped the CGRO with some instruments that were capable of detecting gamma ray burst on board. So they were called the BATC detectors. You had 4 of them onto this CGRO satellite. And this mission is the first game changer mission in the GRB world. This is going to be the change our view of what gamma bursts are. And so you can see that over the course of 9 years of missions, on the right side, on the right panel, I don't know if you see my cursor here. You can see plenty of light curves that have been detected by BATC detectors, actually. You can see, well, you can barely see, but you can see that they have different shapes. Some exhibit some multiple peaks, some have just one single peak, some have one broad peak, etc., etc. They are all different, and this is one of the characteristics of gamma bursts. They are very all different when you look at the light curves. When you look at the spectrum of the gamma bursts, it's completely different. They look more or less all the same, but if you just look at the timing and how these photons arrive to the detector, they are completely different. And over its mission, BATC detected actually more than 2,000 GRBs recorded. So you can understand that here we can make statistical analysis. We can start to make population analysis, so we can start to have more insight into the physics of these objects. One of the most important results of this Compton Gamma Ray Observatory BATC mission is, despite this statistical population of gamma ray bursts that is shown here on this sky map, that is actually isotropic in the sky, which is usually a good insight that those sources are not coming from the galactic plane. So if you remember one of the first webinar we had from the Dr. Robert Neminovs about the great astronomy debate, this was a debate in the 1950 to actually understand if gamma ray bursts were coming from, let's say, galactic origin, or if they were completely extragalactic sources. And it was not clear at that time what was the answer. Of course, it's easier for us now to say, okay, look, this is completely obvious, but this was not actually. And one of the most important results is also shown on the right side. So you have when you take all the light curves of the gamma ray burst, you just compute the duration of these light curves. So you just count how long was the burst, and you arrived on those distribution. And this distribution is showing you 2 broad peaks. So this means that you have some gamma ray bursts that mostly concentrate towards less than 1 second's duration, and you have a large population also of gamma bursts that mostly concentrate in, let's say, 50 seconds duration. And so this was the first hint that actually gamma ray bursts are very likely produced by two different astrophysical scenarios. What we call the short ones are all the gamma ray bursts that are actually populating the left part of this duration distribution. And the long ones are the ones that are populating the right part of this distribution. At that time, we don't really know exactly what are the different astrophysical scenarios, but we barely, we are quite sure that we have two classes of actually gamma ray burst. And this is actually a very, very important result. Now we have a European mission called BEPOSAX. It's our second game changer mission. Why? Because actually this satellite was equipped with X-ray telescopes. The problem of gamma rays, it's hard to localize, and the BATC detectors, they were very bad at localizing the gamma bursts in the sky. So when you don't know where a source is in the sky, well, you are very limited by just the wavelength you are looking at. You can study the gamma ray light, etc., but you cannot say where the object is. You cannot identify a host galaxy that was hosting this GRB. You cannot understand the environment where this burst occurred, etc., etc. So, and you cannot have access also to the distance of the burst through spectroscopic observation with large telescopes. So this really limits your understanding of the source. And so what BEPOSAX brings into the field is to detect gamma burst at arc-minute position. So we had like arc-minute localization for gamma bursts. But what is interesting is that BEPOSAC was not detecting this, very short flash of gamma rays lasting between 0.1 seconds to several tens of seconds. It was actually detecting a long fading X-ray afterglow light several hours after the main prompt gamma ray burst flash. And so this was started to be expected, this kind of things, that something happened, a blast wave is interacting with the circumburst environment and producing a kind of a glow light that is revealing a kind of shock between this ejecta and the interstellar medium. And this X-ray emission is what we got so far at that time, several hours after the burst, or even several days. So we pass from no localization to arc-minute localization. We have now an X-ray counterpart to our gamma burst. We are very happy. And so once you have an X-ray localization at arc-minute localization accuracy, you can launch now optical telescopes, and especially the large telescopes, which have small field of views, even smaller than the telescopes you have. Well, if you take the VLT, it's really a few arc minutes of field of view. Then the Node telescope in the Canary Island, it's also like 6 arc minutes, if I remember well, field of view. So it's very small field of view, so they need very good, at least arc minute localization to start observations. And this is what was done for this gamma ray burst in the 1997, 12, 14. So I may have missed this to introduce this. The way we name gamma ray bursts are coming from the year. So 97 is the 97 year, 12 is December, and 14 is the day of December. And now we regularly add a letter A, B, C, D to say if it's the first of the day, the second, or the third. And so you can see on this picture the optical image taken from this, I think it's a US ground-based telescope, a 3.5-meter telescopes. As you can see that we detected the burst on the 14th of December, and so the first observation in optical was the day after, and almost a day and a half after. But they managed to detect the optical counterpart, and you can see that 2 days after, the optical counterpart has faded away. So this is what was started to be expected by the theory. It's a glowing light that is actually revealing the dynamics, the shocks between the ejecta and the circumverse medium. And as long as this ejecta is actually propagating into the circumverse medium, it's decelerating and you have less and less energy to accelerate particles and make them radiate away. That's why the source is fading away. And so you can see on X-rays, we started to detect the source 6.5 hours after the burst, and you can see that almost more than 2 days after, there is nothing anymore. I have to say that this is not because, for example, here on the left part, the Beposax satellite detected the X-ray counterpart 6.5 hours after the burst, that you had this information 6.5 hours after the burst. So we didn't have at that time a very short latency alert messaging system, and so it was not that easy for people on ground also to catch up these optical counterparts, because we had alerts at very late, very long latencies. Another very important fact for gamma burst, also coming from Beposax, is so you have on the left a gamma burst that have been detected by Beposax, and actually at very soft X-ray, almost in the X-ray domain, even no longer on the gamma ray domain. But what is most interesting for this 980425 GRB is the association of this gamma burst few weeks after with a supernova called 19.8 BW. And this 19.8 BW supernova is now called the canonical supernova that we expect from all long gamma bursts. And this is the first time we associate an real astrophysical scenario to this gamma ray burst phenomena. And so at least some of the long gamma ray bursts are associated with core collapse supernova, with the death of some massive stars. Thanks to Beposax, as I told you, we started to have regular observation on ground by ground-based telescope, usually large telescopes, because they arrived late, and so small telescope didn't have the sensitivity to reach the 22 magnitude at that time. We start to have some optical afterglow light curve that were sparsely sampled, but you can see a few of them here on this plot. And so by the end of the Beposax mission, it's a bit exaggerating, but what we knew is that, okay, GRB are all different in the gamma ray point of view. In terms of, if you look at the light curve from a gamma burst to another one, it doesn't look the same all the time. But they have similar gamma ray spectrum. I didn't talk about the gamma ray spectrum, but you have to know that, they have similar gamma ray spectrum, but they are very different in the timing area. And they are usually followed by long-lasting fading afterglow emission. By long, I mean it's hours to days. For the brightest one, it can last for weeks, but this is the maximum duration you can expect at optical wavelengths at least. And we knew that at that time, some long gamma bursts might be associated with core collapse supernova. And so from this observation, first observation, the GRB prompt emission, but also the afterglow theory starts to be settled and tested for a few hundred of cases. But unfortunately, we had no idea about what happens between the gamma ray flash, between the gamma ray prompt emission and the several hours after we finally detect this afterglow in optical or in X-rays. So we detect the flash of gamma rays, and usually we arrive several hours after to get this afterglow emission, but we have no idea of what is happening between. Another interesting mission, but it's a small mission, but it's a quite interesting mission. The ET2 mission, it's a NASA mission that brought some instruments for which the France was PI also, by the way. And so, just to mention that this mission brought to the field the solidified the association between long gamma ray burst and core collapse supernova. You have an example of what has been detected, a gamma burst that has been detected by ET2 in the 2003. And what you can see on the right side of this slide, it's a spectrum of this gamma burst actually taken several 10 days after the gamma ray prompt emission. And you can see also on the same plot here the spectrum that was taken from this canonical 1998 BW supernova. And you can see that both supernova spectrum match very well. And so this was again a very good association between long gamma ray burst and core collapse supernova. They were able also to derive the type of supernova that is associated to gamma ray burst. For your information, it's type 1c supernova. And so this really solidified this association. What you can see here also is the signal to noise ratio between this spectrum. The 19.8 BW supernova was detected in a galaxy very, very close to us. Very, very, very close. It's the closest gamma ray burst ever detected. And this 29 supernova was actually detected further away. I don't remember exactly the distance, but it was much further away. So you can see the signal to noise ratio for the supernova spectrum is less. Okay, I try to move a bit faster for Swift. This is to me for sure a game changer mission. It's still again a NASA mission that was launched on 2004. Why it's a game changer mission, and I think it's more than that, but actually the legacy of Swift is really unprecedented. It's going beyond the gamma ray burst science. They made science for so many cases in the time domain astronomy and the high energy transients. What they brought to the field is a new satellite equipped with what we call the coded mask. And the coded mask is a technology that allows you to focus, to make image of gamma rays in the sky. This means that you can detect and localize gamma ray bursts or gamma ray sources at arc-minute localization with this technique. This was not possible before to do these kind of things. In combination to this gamma ray detector that is able to detect and localize, you had an X-ray sensitive telescope, XRT telescope, and you had also a UV and a visible telescope called UVOT. And so these two instruments were made actually to follow this so-called afterglow emission, so the X-ray and the optical counterpart of this gamma ray burst that fade away within days to 2 weeks. The most, let's say, important thing that Swift bring into the field, if you remember Bepo-Sax, ET2 was the same thing. We were not able to, capable of having a arc-minute localization very fast so that we can understand what is happening between the gamma ray flash and several hours after during the afterglow emission. What Swift was capable of doing is to make automatic slew on board. Within less than a minute, they were able to point, and they are still, because they are still alive, they are still able to point, let's say, a minute after BAT, the coded mask, has detected the gamma ray burst. This is very fast, actually. In addition to that, they have a system to communicate alert very efficiently and with very short latency. Within less than 30 seconds, the whole world knows the GRB position at arc-minute position. And if the XRT telescope, the X-ray telescope, also detect the X-ray afterglow few minutes after the slew, they are able to communicate actually arc-second localization, like let's say a few minutes after the burst. So this is completely game changer compared to the previous mission. They were able also to perform a lot of target of opportunity observation. So it's a very versatile platform. They are able to slew many times per orbit. So Swift is performing, I think, more than 2,000 slew per TO observation per year. And what is also interesting from this mission, but it's also a kind of general philosophy in gamma ray burst mission, is that the data are totally open source, and so you can have access to all the data from where you want and from who you are, depend even if you are not belonging to the Swift mission. So it's a really, really important mission for gamma ray burst. This is still a really, really important mission for gamma ray burst. So I hope Swift will be kept alive for many years. I'm going to go fast on this, but this is what Swift bring also to the field. So you can see on the left a plot showing you the distribution of the X-ray afterglow that has been detected by Swift over the past 20 years now. You can appreciate what has been brought by Swift by looking at this dashed line that separate actually the space that we had access to with thanks to BeppoSAGs to ET2 satellite. But before Swift, we had access only to late time X-ray afterglow. We had no idea of what was happening before. And after Swift, we got the whole picture of the X-ray afterglow. We were able to build a complete GRB afterglow theory thanks to those observations. So we have now a better idea of what is happening between the prompt and the afterglow emission. We saw some flaring episodes in some of the gamma burst X-ray afterglows, some plateau phases, not for all of these, some very steep decays. So there are plenty of things that are happening at that time, at early times, and thanks to Swift, we had been able to access to those. This is at optical wavelengths. So because Swift is able to communicate fast alert within less than a minute to the whole world, we are able to trigger robotic telescope on ground, large telescope on ground, and so we are able also to now catch the early afterglow, optical afterglow emission. So there are some also interesting features that you can see in the afterglow, in the optical afterglow. And this was only possible thanks to Swift and this quick dissemination of the alerts on ground. So you can see also again on this plot on the left side, prior to Swift era, we only had access to, let's say, the typical standard power law decay we see in many gamma bursts. We had access to supernova studies also. This is the big bump you can see here is the 98 BW supernova actually. And prior and after the Swift era, we also see some very rapid rise and fading behavior of the afterglow that are not seen for all gamma burst afterglows. We see some plateaus sometimes also. It is very rare, but sometimes we see these kind of things. So there are plenty of things that are happening on the early afterglow, and that brings physics and insight on how gamma bursts are radiating away light. So this is really, really a game changer mission. And finally, I want to stress out the fact that because Swift is providing very quickly arc-second-like accuracy localization, this allows us to trigger large telescopes such as the Very Large Telescope, the Grand Telescope Canary in the Canary Island, the Keck Telescope, the Gemini, well, all those kind of large telescopes that are able to take the spectrum, the optical spectrum of the afterglow and derived a proxy of the distance so that we can better understand where those gamma bursts lie into the GRB, into the cosmological history, into the cosmic history. And we can also have understanding of how powerful, how energetic, how luminous they are. This is what is shown in the right panel, for example. This is one of the most important gamma burst relations. So this is, I think, the first correlation in GRB field that students starting into this field is learning at. This is a so-called Amati relation that links together the gamma ray emission that is released isotopically corrected, let's say, during the prompt emission with the peak of the spectrum, the peak energy of the spectrum. Well, these are details, but what you can understand here is that all the collapsar-like gamma bursts, all the gamma bursts that are issued from the collapsar of massive stars are following this blue relation, and all the gamma bursts that are, let's say, from merger of two neutron stars, they are following this relation. So this is really important for us, and this also brings new physics inside. You can also use this kind of correlation to do cosmology, to estimate, for example, the value of the Hubble constant. I won't go into the detail, but these are kind of studies that are actually kind of application to this GRB field. I move quickly to Fermi. This is still a NASA mission, so thanks to NASA to provide also this wonderful mission. Fermi launched on 2008 with two main instruments, the Gamma Burst Monitor, which are these small here scintillators, plastic scintillators, and that actually they are able to detect gamma rays from 10 keV to few MeVs, few 10 MeVs. And you have this big square here that actually hides the LAT the large area telescope that actually detect gamma rays, but at even larger energies, up to GeV energies. And what actually Fermi brought to the field, besides many other things that I'm not going to describe, is that for the first time we actually detected gamma burst not only on let's say what we call the KeV gamma ray part of the spectrum, which is where all the gamma instruments lies detect gamma burst in the KeV energy range. The Fermi LAT detectors was able to also detect the prompt emission at GeV energies. So this is really interesting for us to get these very, very high energy photons to get more ideas about how gamma bursts are radiating and accelerating particles at high energies. And also Fermi brought some interesting insight also that some features are appearing sometimes at low energy. This is what you see on the right part here. It's a spectrum of one of gamma bursts detected by Fermi. And the usual spectrum we have from gamma bursts is the, let's say, this power law shape, the one you see here on my cursor. And from time to time, Fermi detects an excess at low energy here, which is sometimes hard to explain actually. So new components in the prompt emission of gamma burst were revealed by Fermi. This is supposed to be familiar to you, this kind of plot. So also, you know, Fermi is one of the primary actor of the multi-messenger physics in the gamma ray side. I'm not going to go into the details. I think we have discussed that many times, but this is one of the scientific goals also for Kilonova catcher, to be part of this multi-messenger astrophysics. And so you know that in 1708-17, the two LIGO Virgo, the gravitational wave detectors detected the merger of two neutron stars in a binary system, and 1.7 seconds after, we got also a gamma burst detected by the Fermi GBM detectors. We also had our European integral satellite that actually detected this signal. And from those detections, localization of the gravitational wave source was refined. Optical telescope could follow on ground. They finally found what we call the Kilonova counterpart of this short merger of gamma ray photons a few hours after the burst. And we also had a collection of X-ray data, optical data, radio data that show also the afterglow emission from this short gamma burst. So we had the complete picture of what is supposed to be the merger of two neutron stars and what is supposed to happen once they merge and radiate away some gamma rays and X-rays and optical, etc., etc. It was really the textbook case. And it's unfortunately the only case we had so far for this joint multi-messenger astrophysical detection. So I think I'm going to be a bit too long. So I'm going to skip this to go to this last slide, because I wanted to show you actually what we knew maybe let's say a few years ago, let's say 5 to 10 years ago, about gamma ray burst. We had some recent detection thanks to Swift, to Fermi, to also now GWST that is sometimes to time following some gamma ray burst, interesting gamma ray burst, and to all of the ground telescopes that are still keep going participating in observing gamma ray burst. We know that, for example, now what we called before short gamma ray bursts, we should stop calling them short gamma ray bursts, because we have identified some gamma ray bursts that look short, like less than 2 seconds, but we have good clues that they are actually arising from from the collapse of massive star. But reversely, we also have to stop calling long gamma ray bursts because we have found that some long gamma ray bursts actually are really likely coming from the merger of, let's say, two neutron stars. So the field is start to changing to stop calling, well, we still say short and long gamma ray bursts because we usually say that, but we start now to use a new jargon and to say type 1 GRBs and type 2 GRBs, getting inspiration from what the supernova community has made for, giving some types of supernova between type 2, type 1, and then now you have so many types of supernova, but we will stick to two types of GRBs. And from all the different steps that from the very beginning of the progenitor of the gamma ray burst to the way you build a central engine, which is very likely a black hole or a highly magnetized neutron star, and then you produce a collimated jet that is going to produce gamma ray burst and interact with the interstellar medium, produce X-ray, afterglow, optical light, etc. We have question mark on all those different steps. And so even after 50 years of observation, we have these question marks because gamma ray burst observations are not easy, and it's usually very hard to have an homogeneous sample of observation from gamma rays to radios to fully characterize the object and remove the degeneracies we have between different models that can explain more or less the same thing with the dataset we have in hand. So we try to improve the dataset for gamma ray burst. The goal is no longer to detect more, well, let's say like thousands of, tens of thousands of new gamma ray bursts. The goal is now to detect some gamma ray bursts for which we can characterize the full picture from the gamma rays to the radio light. And so here comes the newcomers in the field. So I'm going to talk about SWOM and Einstein probe. So these two missions are actually very recent. The most recent is actually the Einstein probe mission you can see on the right side that has been launched at the beginning of 2024 in January. You can go to the website of Einstein probe if you want to have more information about this mission. The SWOM mission has been launched almost a year ago in June. We have a website in French and in English. You can collect many information, many pictures. We have many media resources, news, etc. So I encourage you to go to this website to get more information. What you have to know then is that those missions are Chinese mainly missions. So the SWOM mission is a partnership between French and China. And the Einstein probe mission is a partnership between the European Space Agency and the Chinese space agencies. So just to be quick, the Einstein probe mission is actually equipped with two main instruments, only X-rays instruments actually. You have two X-ray telescopes that are actually similar to what Swift has on board. You can consider that Einstein probe is equipped with two XRT telescopes. These are the two telescopes, X-ray telescope you can see here. And Einstein probe is also equipped with new X-ray detectors, new X-ray instruments, new X-ray telescopes. Here it's a new technology that allows us to focus more efficiently X-ray photons on the detector plane, which is not that easy to actually focus X-ray photons. And this new technology is called micropore optics, and this is actually inspired from the lobster eyes. The way the nature has brought technology to the lobsters, and their eyes are really amazing in focusing light. So that's why lobsters are very efficient in detecting movement even in dark area where there is not much light. And so we have taken inspiration from nature to build this X-ray optics. So you can see here one of the optics that equipped one of the 12 detectors that equipped what we call the WXT telescope. So this is the wide field X-ray telescope. And this wide field X-ray telescope, when you combine the 12 here modules, they cover at least one of the 12th of the entire sky. So it's a large field of view X-ray telescope. This is the first time we have this very large field of view telescope with such a sensitivity. So we hope that Einstein probe is going to be also a game changer mission at least in the X-ray transient sky. And we have now SWOM, the SWOM mission in the center. So this is the cartoon of the SWOM mission orbiting around Earth. So SWOM is equipped with 4 instruments, and actually SWOM is a kind of fusion between Swift and Fermi, but within a smaller satellite. We are much smaller than Fermi, for example. And so as a parallel, actually, we have a coded mask that is called Eclair, that is inspired by BAT, but we go even at lower energy than what BAT is capable of doing. We have also an X-ray telescope. It's not the same telescope technology than the XRT1 on Swift. This is the same technology than the Einstein Probe WXT micro pore optics X-ray telescope. So we have also a micro pore optics X-ray telescope on board. It's only 35 kilograms, if I remember well, this X-ray telescope. So the way of this technology is performing allows us to have compact X-ray telescopes and very light telescopes. So this is very good. And we also have a visible telescope. It's larger than the UVOT. We have a 40 centimeter visible telescopes on board SVOM. And what we get from Fermi, it's actually the GBM detectors that we have put more or less on the SVOM platform. We have 3 GBM detectors. I show you here one, but you have another one here and another one here. So we have three GRM detectors, while Fermi has 12, if I remember well. And so Eclair is able to see 1/6 of the sky, and GRM is able to see half of the sky, if I remember well, instantaneously. So why did we do that? To put some GBM detectors on well, these are not the really GBM, and we have developed new ones, but this is exactly the same technology. And the reason why we wanted to have Eclair and GRM on the same platform is that actually BAT is very good at localizing, detecting gamma ray sources, but it's quite bad at constraining the gamma ray spectrum of these sources because the energy range of BAT is very narrow. While GBM is very bad at localizing the sources, but it's very good at characterizing the gamma ray spectrum. So what we wanted in the SVOM platform is to combine the two success of those mission, be able to localize very accurately down to arc minute localization the gamma ray burst, and to also constrain the gamma ray spectrum by combining the Eclair energy range with the GRM energy range. And we also keep the philosophy of Swift with having X-ray and visible telescope to follow the X-ray afterglow and optical afterglow on board in real time. This is really important to keep this capability. I'm going to show you the movie of the launch of SVOM. If you didn't saw it, it was very incredible moment for all of us. This is very small, so I'm going to enlarge the screen if I can do it. Maybe I have to exit the presentation mode. I hope you still see my screen.
Yeah, we can see it.
Yep. So this was the launch. I was there. Actually, it was in launch in China. We were like 3.5 kilometers away from the rocket, so very, very close. And so it was a very impressive moment for all the people there. And so we were all afraid of what could happen at that time. And probably the most stressful moment for all of us is when the rocket is going above the clouds and we could not see anymore the rocket. And so we just had to pray that nothing wrong is going to happen. But well, everything was successful, so we were very happy, but it was a very intense moment. And what was interesting is that we were very close to the rocket, so we could hear the noise. It was really crazy. So those two missions, SVOM and Einstein, they have been put in low Earth orbit, so they are orbiting at 600 more or less kilometers in altitude. They have an inclination orbit with respect to the equator plane of about 30 degrees. And so they make one orbit around Earth in an hour and a half, more or less. We have also a very specific pointing strategy. So this means that we have a kind of anti-solar pointing strategy for both missions, actually. So this means that half of the time we have the sun into our back. So our instruments are never pointing towards the sun direction. So this was made to optimize the follow-up detection on ground. Once we are going to detect gamma bursts, we are going to detect gamma bursts during the night side. Swift, for example, is able to detect gamma bursts close to the sun, but most of the time these gamma bursts cannot be followed on ground, and so they are lost for science. So we've changed this. We had a very specific anti-solar pointing strategy. And you can see the track of the satellite on Earth. They are orbiting actually between plus 30 degrees in latitude and minus 30 degrees in latitude. I'm showing you here some tracks of the SVOM satellite, but I mean, the Einstein probe is exactly following the same orbit, so it would be the same tracks. I'm going to be fast, so I had wanted to show you what is the typical wise worm, and my Einstein probe is the same. It's a powerful transient detection machine and alerting detection machine. This is completely inspired from what Swift has done for 20 years. But we try to reproduce that. Believe me, it's not that easy to make real-time detection on board, transfer the information on ground, distribute it to the whole world, etc., and trigger follow-up observation. It's a very precise machinery, and a little grain can break everything actually. And so you have the whole full picture here of what is happening once a gamma burst is detected on board at T0. Usually we are able to communicate on real time with on-ground radio antennas that communicate in real time with the satellites. You can see the visibility horizon of these radio antennas, and that allow us to communicate alerts within 15 seconds through the GCN NASA system, which is the system that the professional and also I think the amateur community is using to get the information from GRB detections. It usually takes us 2 to 3 minutes to stabilize and slew towards the position of the source. It usually takes us, once we detect the X-ray counterpart, few minutes, let's say 5-10 minutes, to have the first accurate arc minute down to several tens of arc second localization accuracy with MXT, our X-ray telescope on board. And it usually takes us like half an hour to an hour, or it can be even several hours, to identify the optical afterglow thanks to the VT observations. And once a gamma burst is detected on board, we start a clock, and so we stop the automatic alert sequence. So this means that the satellite, and especially the MXT instrument and the VT instrument on board, they stay observing the burst for at least 5 orbits. So during approximately 8 hours, we stay on the burst, and if there is another things to happen, we stay on the burst. So keep in mind that SVOM is able to distribute alerts within few tenths of seconds. Einstein probe is also the same, and so these are this kind of legacy we got from Swift and Fermi missions actually. I'm showing you a movie of the transient sky seen by SVOM so far since the launch. You should see 2 colors appearing on this sky map. You should see yellow colors that mostly cluster into the galactic plane, and you should see black points appearing somewhere randomly in the sky, more or less isotropically. And so if you got this map, let's say 20, well, it's even 30 years ago during the great astronomy debate, you would even, you could argue that these black points are not coming from the galaxy, they are coming from the extragalactic origin. The yellow points are coming from the galaxy or not. Well, this was the great debate. We know that now the black points are really cosmological gamma bursts. They are coming from outside of the Milky Way. And the yellow dots are actually galactic sources that inside our galactic plane. But it's sometimes not easier. Not all the yellow points are clustered in the galactic plane. You can see some points from time to time that are, let's say, at high galactic latitudes. And these are actually some flaring stars we detect from time to time, or some, well, we think that these are flaring stars actually, that we detect from time to time. And these flaring star or this nearby star are very nearby to us, and they are distributed over a sphere around the Earth, let's say, horizon, and in a kind of halo around us. That's why we do not detect this source necessarily in the galactic plane. All the yellow points we have in the galactic plane are actually X-ray binaries. What we call X-ray binaries are a central compact object. It can be a neutron star, it can be a black hole that is actually getting matter absorbing matter from a companion star and radiate away X-rays, optical lights, etc., etc. So these are mostly the types of sources we are detecting in the galactic plane. And so the green, the blue, and the purple points are GRBs, but from different types. What we call the short ones, let's say the merger of two binary neutron stars. The green ones are the collapsars, gamma ray bursts, so that burst, we think that they occurred from the death of massive stars. And the purple ones are a kind of subclass of long gamma ray burst, of collapsar burst, called the X-ray flash of X-ray rich burst, mainly because they are mostly seen in X-rays and not in gamma rays. That's why we call them X-ray flashes or X-ray rich burst. So far, since the launch of SVOM, we have detected 127. This number is not totally up to date. I think we are now at 130 bursts between the Eclair and GRM. The GRM is detected much more gamma ray bursts than Eclair because the field of view of GRM is larger than the one of Eclair. And we had to switch on, switch off Eclair more frequently than GRM since the launch. So that's explained also the difference. What is interesting is that a significant fraction of the bursts that are detected by SVOM are also detected by other missions. It can be Einstein probe, it can be Swift, Fermi, etc. So this is really interesting for us to also have this joint detection because we can cross-calibrate our instruments and we can also extend our energy range to lower energy range. For example, if WXT from Einstein probe is detecting the same burst than us, they will detect it mainly in the X-rays, and we have barely X-ray capability with Eclair, but the WXT is going down to very soft X-ray. So this is really interesting for us to have this joint detection. You have the redshift also. We have some redshift for some of the gamma ray bursts. So the redshift is the proxy for the distance of the event in the universe, and so it's really important to have this information. I'm not sure if I have time to go into the details, but why SVOM and Einstein probe can be new game changer missions in the field? Mainly because they are equipped with new instruments that are going to look at gamma ray burst at different, let's say, the same energy range than before, but they kind of extend the energy range on which we are observing gamma ray burst, mainly down to X-rays. And so, for example, if you want to ensure that a short gamma ray burst is actually from merger origin, so two neutron stars that fuse together, collides together, and produce this sharp spike of gamma ray photons that you see, for example, here. This is the short gamma ray burst detected by SVOM on August 21st last year. You can see this short spike lasting less than 2 seconds, but it is also followed by this kind of emission tail that is well known now. Well, well known, not well understood, but well known in some fraction of short gamma ray bursts show these soft emission tails. We think we have some astrophysical scenario to explain this. After the merger of the two neutron stars, you can have some material that fall back into the let's say remnant compact object that has been formed after the merger of the two neutron stars. It can be a high mass neutron star or a black hole, and so some materials can fall into it and just be reprocessed into gamma rays afterwards. This can be this, or it can be another scenario, but this signature of a very short spike with the very soft emission tails seen very barely in gamma rays. And this is what we have for the GM detector that mainly sees the short spike here, but mostly nothing after. No emission tails seen by gamma GM detectors after, because here the emission is compressed between 5 to 6 keV, and GM detection start at 15 keV, so they are not able to see this kind of extended soft emission. So this is one clue to identify the real merger of two neutron stars that are producing short gamma ray bursts. I'm showing you here, but I know the plots are quite hard to see. Another short in terms of duration, like less than 2 seconds, gamma ray burst detected by Fermi GBM, but also detected by SVOM GRM, and a Russian mission called Russian NASA mission called Conus, and with the wind instrument. This is the light curve of wind you can see on the left part here. You can see this sharp spike of gamma rays, followed by this tail again. But in this case, this tail is not really soft. This means that this tail is really seen at regular gamma rays energy range. And when you put this burst into this so-called, if you remember this E-iso, this Amati relation that separate the collapsar GRBs on the gray side here to the short merger GRBs, the blue and the red points, you can see that our burst, if you take the duration of the burst on the spectrum, is lying into the short merger area. However, we have good hints, good clues that this burst is actually occurring, has been produced by the merger, not the merger, the collapse of a massive star. Mostly because this tail is not soft, and we think that it's just an extension of this main spike, and this is still the gamma ray burst that is occurring within the jet. This is not fallback accretion material onto the black hole. The multi-wavelength follow-up have provided a redshift, and this is a redshift of 2.6. Maybe it's mean nothing's for you, but it's very, very far away. And we usually never see merger so far away because they are usually quite fainter than long gamma bursts. And so if it's really a merger of two neutron stars, it would be the highest redshift at the highest distance for short gamma burst ever detected so far. We don't believe this is the case. We got GWST photometry also for this burst, and especially for the host galaxy. And this host galaxy properties really lies into the collapsar model. These are star-forming galaxies with low metallicity, and this is really what we expect from the galaxy that host gamma bursts that will be produced by collapsars. So it's really collapsar origin that is favored, but you can see you have two kind of same burst, short burst with a short spike. The tail is not really the same, and in one case it's a collapsar, in another case it's a merger of two neutron star. This is showing you also how diverse is the GRB population and how deep we have to go into the analysis to identify the origin, the astrophysical scenario behind the gamma ray emission. This is what I was talking about before, a new population of subpopulation of long gamma burst that is called X-ray rich and X-ray flash burst population. You can see here a detection by SVOM eclair on the top panel at different energy range of gamma burst it was in October, the 1st of October last year. You can see the signal is appearing between 4 and 20 keV energy range in gamma rays, in soft X-rays, let's say. And you have nothing after, let's say, 50 keV, which is the regular gamma ray energy range where we detect usually gamma ray burst. And this very soft X-rays burst is a totally new population that is poorly explored. It has been already seen actually by Beppo Sachs, ET2 with few events. But we think that SVOM and Einstein probe, as you can see another example of an X-ray flash burst detected by Einstein probe on the bottom panel. We really think that Einstein probe and SVOM are going to populate this area of the Amati plot with low isotropic energy released during the gamma emission and very low energy spectrum into the X-rays. So here, this left part of the Amati relation is actually should be populated by bursts that are mostly seen in the X-rays and have low energy output. This is quite new, and we try to explore this now. I will skip this slide. I will go to this exciting detection we had so far in March this year with FOM. We detected what we call a high Z burst, so a burst that is really, 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 really far away in the universe. If you look at the left panel, you would see a detection from Eclair, from SVOM. It means maybe probably nothing to you, but well, if me, I'm looking at this sky image, sky reconstructed image of this gamma ray source, I just see, okay, it's a regular gamma burst, it's okay, there is nothing very peculiar about this. But when we investigated more with the VT telescope on board, we didn't detect any optical counterpart at very deep sensitivities, 23, 24th magnitude. When you do not detect such a thing, it can happen that the optical light is totally absorbed by the dust in the line of sight. in its host galaxy or by our Milky Way galaxy dust. But in this case, it was not the case. And so we triggered very large telescope observation. And so it turned out that this gamma ray burst was a very, very far away gamma ray burst. So the non-detection by the visible telescope was explained by the fact that the burst was so far away that the light, the optical light, was too faint for being detected by the VT telescope. I placed this, well, not myself, thanks to my CI colleagues who produced this plot actually. We placed our gamma ray burst detected by them in the, let's say, the population of the high redshift gamma ray burst. It was the last high Z burst was detected in 2012. So it's been like almost 12 years we were waiting for a new detection of this kind. So, and these bursts are actually long gamma ray bursts, so occurring from the collapse of massive stars, but at such high distance. When the universe was so young, these actually explosions are coming from the first generation of stars. And what is interesting for us is that these bursts are so luminous that their light can be emitted at when the universe was so young, propagate towards us and give us information about what was the property of this young stellar population, about the host galaxy environment, etc., etc. So it's a very rich information we get from these rare events. So it's been the fifth further distance, larger distance GRB ever detected. We were waiting that for 12 years. And so we hope that we will get more in the future. You can see that we detect this burst when the universe was approximately 405, 6, 7 million years aged. And so this was really the first generation of stars that we have detected exploding now. I'm going to finish this long webinar, I'm sorry, with what KNC can bring into this field of research. I think it's we got some question in Slack. What would be the best observational strategy for gamma ray burst? Because sometimes, as you know, gamma bursts are fading away quite quickly within hours to days. So what is the best way to do? I will try to answer to those questions now with 4 slides. And I will start to come back to the optical afterglows because this is mainly where we are going to act. You can see we are going to help to study the GRB afterglow emission. So after the gamma flash has been produced and the jet is interacting with the interstellar medium. And you can see on this population of known gamma ray burst optical afterglows where our discovery potential is for Kilonova catcher, according to me. Because the left part that has put as a kind of area that is not really accessible to us, especially at very short latency after the prompt emission. I'm talking about tens of minutes. I think you have to have a robotic telescope answer robotically to these VOM alerts or Einstein probe alerts to catch these very early phases of the GRB afterglows. We, I think, don't have this capability in KNC because we are answering by hand manually to the alerts. So that's why it takes time for us to set up the observations, set up your instruments to be ready to observe. So I think it takes hours to do it. Maybe it can take shorter for people who are using remote telescope in telescope farms. And of course, below this 20-ish magnitude limit, this is the world of large telescopes. It's a bit arbitrary. I have to confess that some of you are able to reach 21st magnitude. But let's say that the 20 magnitude is our limit. And so you can see that our discovery space is not that limited. It's limited, but it's not that small. And actually, the first thing I would say is that the GRB afterglow, they always, if you want to study them from the beginning, they require very fast observation. And this is mainly done by robotic telescope. I think this will be probably not done by us. But in the second time, we can, from our side, try to catch the, let's say, hours after the burst the optical afterglow to catch the standard, what we call the standard forward shock decay. There will be possibility also to catch the supernova associated with very close long gamma bursts. This is what you can see here for this bump here from 1908 BW supernova. This is another bump from another supernova from another gamma burst. So there is room for discovery for us and to participate. This is just that gamma burst has a big problem. We never know in advance if a gamma burst is a very interesting burst or not. I can't tell you from the gamma ray detection if a gamma burst afterglow is going to be peculiar, if it's going to show flare, if it's going to show plateau phases that were not expected, if it's going to be bright or faint, if it's going to really show interesting features that we should capture with our observations. I can't tell you in advance. That's the big problem with gamma ray bursts. You have to go for all of them and then you have to realize that, okay, they are interesting, but you have to spend time to observe at first glance to have your first opinion on it. And so it's hard for me to tell you, okay, this burst is interesting or not. I can tell you it's interesting or not based on if there is a bright star around the burst or if the moon is not so far away, etc. These are observational conditions, but in terms of physics, it's hard for me to tell you. So why? Sometimes we won't be able to, make a very good light curve sampling, etc. So sometimes we will be able, sometimes not. It's still very important to at least catch one optical detection point. Why it's so important? It's because we want to go from photometry here it's an example from what has been done from this high Z burst. From this point, we want to also then trigger a very large telescope to catch the spectrum of this optical light, to identify how the light is produced, what are the different absorber materials in the line of sight, etc., and to make science with this spectrum. These spectrum are taken with large telescopes that have very, very small field of view. So they need us to provide arc-second localization of burst. So even if we are not able to, study the GRB afterglow emission by sampling the light curve, at least if we manage to get arc-second localization, we can warn the very large telescope so that they can have a try. If they measure the redshift, it's a big win for all the GRB community, because this GRB would be able to have further analysis, further studied, because once we know the distance of an astrophysical object, we have a lot of information on the physics then. It's important once we have this detection point to quickly report it in the GCN circular. We have talked with Christina yesterday, and so I think we will give you maybe a plan for the Kilonova catcher community to produce quick GCN circulars. We need to work on that point to be better on this, but it's okay. It's a work in progress, and we will do better once we will be ready. But we'll try to be ready by this summer at least. It's also important sometimes to provide upper limits, but only if your upper limits are deep. By deep, I mean, let's say R-band 21st magnitude. In the first 12 hours, it's kind of good. If you look at the GRB afterglow population, if you go to 21st magnitude and you arrive, let's say 12th hour is something like here. And if you do not see any gamma bursts, you can see that most of the known population is above this line of 21st upper limit magnitude. So once you got the 21st upper limit in short latency, I would say to less than 12 hours, it's kind of good information. It can help us usually we detect the X-ray afterglow, and it can help us also to understand what is the difference between the flux we see in X-rays and the flux we should see in optical. And sometimes it's completely at odds with what we expect from the standard GRB theory. So upper limits are also useful for this kind of science. They can reveal IZ GRB candidates sometimes, but for this, I think 21st magnitude, you have to go very, very quick to provide insight that the burst is probably a high Z burst. You have to populate this region of the time space, which is like few hundreds of seconds or few minutes after the burst. And so most of the time we don't have in Kilonova catcher the aperture size to collect enough photons to have 21st magnitude in 1 or 2 minutes. That's why I'm saying this is the large telescope world here. I'm going to stop here. I'm sorry it was a bit long with my take home messages. I will let you read the first 4 points and I will just comment the fifth point, which are my advice in terms of how we should proceed for gamma ray burst afterglow observations. So first of all, sorry, it's important to favor, if you can, if you cannot have color filter observation, just go unfiltered, it's okay. But if you can favor colored observation, for gamma ray bursts, they are usually red sources. And so we usually favor red filters. So R and I Sloan filters or Johnson Cousin R and I filters are the best, I would say, to observe gamma ray burst. You can have a try with V filters or G-band, it's okay. But sometimes if the burst is too far away, the light is going to escape from your photometric band and you would see a drop of the flux very quickly in the G and the blue bands. That's why we favor more also the red bands. It's because GRBs are cosmological sources, so they are very far away and the spectrum is shifted toward the red wavelengths. And so if the burst is too far away, you may just provide upper limits in the G-band. First point, if you are able to observe within, let's say, 6 hours after the trigger time, after the burst, after you receive the notification, the alert notification, I would advise go for it, no matter what information you already got. Well, if somebody has already put 22, 23 upper limits, okay, obviously you don't go. But if you have no information or if you have barely seen something in the GCN circular or if we said something before, I would advise to go, just go. If you are able to observe between 6 to 12 hours, let's say after the trigger time, I would say that, well, in 50% of the cases, you should be able to catch the optical afterglow. Maybe not producing very well sampled light curve of the optical afterglow, but at least you might be able to produce a detection point that will be useful for the large telescope to get then spectrum and redshift measurement, etc. So this is still important if you can be here in the 6 to 12 hours. Of course, during these 6 to 12 hours, other observers may have reported the upper limits. If it's too deep for you, you just don't go. I will try to, for each burst, to say no go or go if I manage to read all the GCN circulars on time, but really feel free also for you to the whole KNC community to reach the GCN circular website. We have provided a link into the observation channel into our Slack towards this GCN circular website so that you can read all of the observational reports that have been produced by the GRB community. And if you are able to observe only 12 hours after the trigger time, I would say don't rush, wait for information and decide to go or not, depending if someone has already reported something on the GCN circular or if some of the KNC observers has already reported some detection or not in our observation channel. And if you are 24 hours, if you can't observe the first night, you're going to arrive very late. I would advise to just wait for more instruction. Usually after 24 hours, we just stop the follow-up campaign for gamma burst. But we don't know, sometimes gamma burst is going to be measured with a very close redshift, so it's going to be very close to us. And in this case, we might be able to catch the supernova later weeks or days after the burst, well, usually some weeks after. So in this case, this is what we did for 20, I don't remember its name. 12, I don't remember, but we tried to catch the supernova from a 0.4 or 3 redshift burst with some of the KNC members. We failed, but we had very, very interesting upper limits. And there will be a publication about that. I will come back maybe later on Slack about this, but so after 24 hours, the only thing we expect is maybe to get supernova association with long gamma burst. After 24 hours for the brightest burst, we may have a chance. If you look at this, 24 hours is here. You can see that there are very few bursts that will be still bright enough for us after 24 hours. So that are my advices right now for now. Favor red bands, and depending on where you are in the timeline of the burst detection, you can get the decision to observe or not. Of course, we can discuss that in the observation channel, in the Slack, in our Slack, and I will try to keep people updated on if the burst is interesting or not. But really, when the detection occurred, I have no idea if the burst is interesting. So if you have, thank you for your attention and sorry for being long. And if you have any questions, I can answer also, or comments.
What a great presentation. Thank you, Damien.
I may have to mention for the French people that actually we have read a book about the SVOM history and let's say how the mission has been built. I can provide the link. We have, I think, a numeric version, numerical version of this of this of this book. So I think it's not in an English version. I'm sorry, but okay. Was just to mentioning because all the cartoons you can see here are extracted from this book. It's a drawing book.
Also, I will be adding the GRB follow-up strategy, a lot of what Damien talked about in his presentation to the manual sometime this week. So guys, so please keep an eye out for that update. I do have a question, Damien, about your being present at the launch. What was your involvement with that? With the launch, with the setup? How did you partner with the development of that? How are you involved in it?
Of what? Sorry, I missed the
The
first
the the SVOM launch, the SVOM launch. What was your involvement?
Uh, I was mainly a tourist watching for this. No, actually, we organized the scientific meetings a week before the launch with our Chinese colleagues, with the kind of core team of scientific people involved in both the French side and the Chinese side of the SVO mission. So we were actually trying to define the last, the last steps to organize the science discussion and what is going to be the first action to do once the SVOM is going to be actually operational. So we were, I think, 60 people there, 60 to 70 people there in total. And after the launch, we had 1 week of meeting to see if everything was okay. Every day something crazy happened. We had to deploy the solar panel. We prayed that everything was working well. The power on board was okay. Then we turned on the radio antenna that is designed to communicate with the ground-based radio antennas. Everything was working well. We were very happy about that because we were very worried. So we organized all those tasks the week after the after the launch. My responsibility inside SVOM is to organize the scientific operation of the mission. This means this is something I didn't talk about, but this is something Swift, Fermi, and other GRB missions are doing. We are automatizing a lot of things, but behind the scene, there are humans in the loop that have to check the data in real time, take decisions for triggering follow-up or not, as we do also for Kilonova Catcher. And so we have these so-called burst advocate people who are on shift to check the data. And so I had to write all the working procedure for all the SVOM burst advocate scientists, and I have to ensure that actually the BAs are understood their role, what they have to do, and it's actually a very important role because without these guys, the scientific return of each follow-up campaign can be 0 to crazy things. So that was my most implication on this. I was mostly involved in the scientific operation, and so I was invited to the launch for this.
That's really cool.
And we were very close to the rocket. That's why it's crazy. I mean, the bus just drive us like I think I passed like a few hundreds meters close to the rocket. So but that's crazy. Full of gas and full of
How did it feel? Because I was at one of the last space shuttle launches, Kennedy Space Center for the Atlantis. I even have it on my jacket. Oh, yeah, right here. When I saw the
Yeah,
Atlantis, and you could feel it. And we were miles away, and you could feel the percussive, that
yeah.
compound wave of amount of energy being used to get out of Earth's orbit. How did it feel being in the mountains? One, because South Northern Florida is flat, and we're on the coast, so we
Yeah.
felt it directly. But how did it feel being in the mountains? Did you feel that percussive response?
Yeah, and yeah, we feel the vibration of the rocket of the engine. The sound was crazy because we were so close. And so I think with the mountains also, maybe probably the sounds is bouncing from the mountain to you, etc., etc. So you well, it was a kind of crazy environment. Well, you launch a rocket in the middle of mountains, so that's quite nice. But
That's so cool.
yeah, and so we didn't expect to be so close actually, and so that's
Yeah.
the really interesting thing.
Yeah. With all these missions, we kind of know the answer to this, but with all these missions, Fermi, Swarm, Swift, we see every few years a catalog come out. We have the 2009 Senko one. We have Alexander Kahn's catalog or models. Is there anything being done now with these new missions to kind of aggregate this data into one catalog?
This is the plan, yes. We have the plan to produce and this is one of the goal of the GRB missions, the SWOM mission actually, also in Steinprobe. So one of the goal of the SWOM mission is we are going to detect much less GRBs than Swift and Fermi has ever detected. We are going to detect about 60 bursts per year with Eclair. Swift
Hmm.
is around at 100 bursts per year, and Fermi is at around 250 bursts per year. So we are going to detect much less bursts. But our goal is to characterize the prompt emission with both Eclair and GRM very carefully, and also the afterglow thanks to the VT and MXT and all the ground-based telescope we have set up on ground that are
Hmm.
dedicated to respond to our alerts. And so the goal of SWOM is to produce an homogeneous data set for a catalog of birds that will be released every X year. I can't tell you
Hmm.
because the first year here it's quite hard for us. We
Of
still have
course.
work to do to calibrate
Yeah.
all the analysis, etc. But yes, we will produce this catalog publicly available with data, etc. So yeah. But
Yeah,
our goal
that's very
is really to
interesting.
make also the transition between the prompt and the afterglow emission very smoothly and to
Hmm.
extract most of the information we can do from every follow-up campaign. This is the goal. This is not easy, and we don't manage to do it every time, but this is the goal.
And is it going to be so I guess this also is the same question another way. Um, so SWAM will detect or observe much less than Fermi or Swift. But is there any formal overlap? Uh, or is there any form we have the general coordinate, we have the GCN system, but is there any formal overlap or communication regarding these events between the three missions?
Yeah, so we have set up an automatic link between SWOM and the Swift mission, for example. So once SWOM detect burst, we immediately trigger target of opportunity observation from Swift to get observation with not with BAT, but with XRT and UVOT for our burst. And reversely, when Swift is detecting a burst, we automatically trigger target of opportunity so that our VT telescope and MXT X-ray telescope can also directly follow up the sources. We don't have such a direct link in real time in space because space agencies like to have information go back, check if this is
Yes.
doable, and then just upload it. But I think the next we are thinking about next generation of mission already. And so we are thinking of producing now constellations of satellites that are interconnected but in space with no mission center in the loop, and they can discuss each other and take decision automatically and autonomously. This is going to be a next game changer, I guess, in the field, because then you don't have mission center in the loop, and so you are completely autonomous. But this is the way people are thinking, and this is what Swift team also has proposed as kind of new kind of concept of mission for this camera burst studies, for example.
It's nice to see everybody playing well together.
And we also played with the Einstein probe mission, of course, because we are
Oh,
actually
awesome.
we are made, well, I mean, we are operated by the same mission center. So these are the same people who are operating the two satellites. So we have set up the link. And
That's
also
cool.
Swift have made the link between EP and so this, I would say, three missions, Swift, SWOM, and EP are really working closely together. Fermi has no slew. Well, Fermi is not going to slew because there is no X-ray or visible telescope on board Fermi. So what we just do with Fermi is cross-matching the alerts and just
Mhm.
trying to see if we see the same sky at the same time, but that's all.
Very good. Awesome. Thank you so much, Damien. Do we have any other
And we are
questions?
connected to gravitational waves also now. So
I mean,
everybody is
that's
connected
that's
together. That's the time domain astronomy is kind of everybody's connecting each other to the
yeah,
real challenge of these coming years is to really be able to, we are cross-matching so many alerts between them, so that now we have to ensure that we extract science from these many cross matches
yep, that's
and not
true.
be messing up in
Nope.
these things. But yeah, that's the goal.
Wonderful. Damien, please send me your slides when you have the chance.
Yep.
And are there any more questions or comments? Alrighty. Well, thank you so much, Damien. What a great presentation. Really informative. I'm sure all the members are really happy to get this information and to have it translated so nicely. I know I appreciate it.
I got I see the comments. I just got your message, Eric. Yes. Yes, okay. More feedback on the GRBs you already observed. Yes, this is something I plan to do by June if I can. Actually, I was focusing on other tasks these past weeks, but yes, I plan actually to provide this feedback for the past GRBs we observed. And I think with Christina, we are going to provide you also some instruction for GCN circulars. We have to discuss with Christina before giving you, but I think you are going to be able also to publish as a group quickly, so that would be great.
Yeah, and I will send an email about that soon. So wonderful.